Morning, buongiorno. Sentite, vedete?
Buongiorno, sì, la vediamo.
Ok. Waves in plasma. We've been looking last Friday at electrostatic waves. So we start from there, briefly recapitulating what we were seeing. So we are dealing with longitudinal waves, so waves in which the wave vector is parallel to the electric field, or vice versa, obviously. And there are waves in which the electron means is the electric field is propagating in the plasma, whereas static means that the B is not propagating. And the fact that B is not propagating comes from the fact that actually these waves see that the electric field oscillate in the same direction of the wave. So the source term for the B field is actually 0. So the perturbation of the magnetic field, whatever it is not propagating. And in order to obtain the dispersion relation for these waves, we use 3 equations. One for the motion of the electrons, which are the particles that are involved in these electronic electrostatic waves. Then we have a source term for the electric field. So we use it in Gauss law, which combines the electric field in the plasma with the charge unbalance inside the plasma. So this is coupling the dynamic of electron oscillation together with the sources of electric fields, which in turn determines the motion of the electrons. And in order to close the set of equation, we used the continuity equation, telling us that from each volume of interest, we are balancing exactly the number of electrons that are entering and exiting the volume of interest. So we project all the equation into the direction of the wave. The direction of the wave is represented by the k vector, and we look for a solution in 1D. So we look for plane waves in which the electric field and the k vector are parallel to each other. So we linearize of the equation, the dynamical equation, and we move to the complex notation. And when we end up with, okay, this is the algebra, we go to this dispersion relation, which is, as you might start to remember now what the dispersion relation is a relation between the omega, the angular frequency of the wave, and the k vector, or in this case, the wave number of the wave. So only pairs of omega and k that satisfy this relation correspond to a wave solution. So a wave that actually can propagate in the plasma. And we recover the dispersion relation that we introduced at the beginning when we were studying this relation. So we notice the presence of the plasma frequency here. And there's a term here arising from the fact that electrons are taking part into the process, and this is a characteristic velocity for the electrostatic longitudinal waves, and is very close to what is the thermal velocity. Okay, we'll check that in a second. So we left our derivation here, so where we can start from here. This is the 3rd of May 2021. And we were sketching this dispersion relation and commenting the various parts of this plot. So here is the dispersion relation, is the usual smooth curve that asymptotically goes as the phase velocity. So we see that this kind of asymptotic solution, see for instance that this solution for positive k goes as V0e times k, and which is representing the progressive solution. So it's moving towards positive x, and the other one is the regressive one that goes like minus V0e times k. For very short wavelengths, so for very high k numbers, we see that the dispersion relation becomes that one of a straight line. So the non-dispersive part of the spectrum or in wavelengths. So we see that at very short wavelengths, the plasma is not dispersing. So it's the wave packet can propagate in the plasma without any dispersion and distortion. Whereas when we go to very long wavelengths or very short k numbers, so when k goes to 0, the dispersion relation departs from the straight line and goes to 0. Actually, it's not going to 0, it's going to the plasma frequency. What it goes to 0 is the slope of the dispersion curve. So let's recall what is the property of this function, and from the dispersion relation, we can recover both the phase velocity and the group velocity. So we see that the phase velocity is equal to omega divided k, and omega, we can get it from the dispersion relation, is the square root of omega squared of the plasma frequency plus V0 e squared k squared, and we can bring inside the square root the square of the wave number. So we end up with that the phase velocity is V0e times omega e squared divided k squared, square root, and we can take a velocity out of the square root. So we see that the phase velocity is V0e, the characteristic velocity for this kind of waves, which multiplies 1 plus omega e squared divided V0e squared k squared. And as k goes to infinity, this term goes to 0, and we see that the waves are traveling at the characteristic speed for longitudinal waves. So this, let's remember what this is. This is the square root of gamma kb t over me, and is the characteristic velocity. Of electronic electrostatic waves. How does this compare to the thermal velocity? Let's recall what the thermal velocity of the electron is. So let's, the usual argument is 1/2 mass of the electron, so the average kinetic energy, the thermal velocity of the electron is the root mean square. The thermal velocity is the root mean square velocity of the electrons, is connected to the average kinetic energy of the electron species, and we can get that from the equipartition theorem. So we have electrons which are point masses moving around, so we can approximate to a monoatomic gas, the electrons. That's a good representation for them. And a mass point has got 3 degrees of freedom, so we have that the mean contribution to the energy is 1/2 kBT for each degree of freedom. And if you remember, this is the way we already defined in our lectures the thermal velocity. So we can solve for the thermal velocity of the electrons. Squared is 3 kBT over ME. And as you can see, this is the characteristic velocity of electrostatic waves is very close to the thermal velocity, same order of magnitude. The only difference is that here we have a factor of 3 in 3-dimensional space, and here we have a gamma. Then for, if you remember, for a monatomic gas, gamma corresponds to 5/3, which is 1.67. Okay, so there's a slight difference square in due to this factor, but basically they are representing more or less the same characteristic velocity. So let's have a look at the last velocity we are interested in. So we have the phase velocity, we've seen the thermal velocity, and now let's check what is the group velocity for these waves in plasma. And let's remember that the group velocity is the velocity at which information, energy, momentum can be are traveling in the medium, so they can be transported by the wave phenomenon. So let's look at the group velocity. If you remember, what is the group velocity? Is the derivative of the dispersion relation. Okay. It's easy to express our dispersion relation here as omega as a function of k. Let's take the square root of it and then do the derivative. But another way is very easier to do, is to differentiate this relation and from that get the group velocity. So let's start from our dispersion relation here, which is omega equals omega plasma squared plus V0 E squared times K squared. If we differentiate this, then we get 2 omega d omega on the left hand side, and we can then we differentiate the second term, and the second term becomes V0 E squared times 2 K dk. And now let's get dk on the left hand side and put everything on the other side. So we get d omega over dk equals, obviously 2 goes away, and what it remains is V0 E squared times K over omega. and k over omega is equal to the phase velocity. So this becomes V0e squared times V phase that we just obtained before. And you see that this ratio here actually has the dimension of a velocity. Now we can plug what the phase velocity is, and we see that that the group velocity becomes V0e squared divided V0e square root 1 plus omega p squared over V0e squared k squared. Is that correct? Yes. So one of these goes away, and we end up with V0e divided the square root of 1 plus omega p squared divided V0e squared k squared. And we see that when k goes to infinity, this term goes to 0, and the group velocity goes to the same limit, which is the phase velocity, which is the characteristic wave velocity. And when k goes to 0 on the other side, this term goes to infinity, and the group velocity goes as a finite number divided infinity, so it goes to 0. So we can summarize our group velocity here, which is V0e over 1 plus omega p squared over V0e squared k squared. I just copied the last line, and for the group velocity goes to V0e for k going to infinity. It means it's the same as saying that the wavelength of the wave goes to 0, so very short wavelength, and the group velocity goes to 0 when the wave number goes to 0, so the wavelength goes to infinity. Okay. Let's go back to our plot here. What is left? We observe that for a cold plasma, so when we have a cold plasma approximation, you see that the characteristic velocity, where is it? Is the, is related to what? To the temperature. So when we go in cold plasma approximation, the temperature goes to 0, so it can be neglected. So the thermal velocity of the electron goes to 0. So what we get in that approximation. So cold plasma approximation, we see that T of the electrons goes to 0. In that case, the characteristic speed of these waves is going to 0. And our dispersion relation becomes omega as a function of k, becomes omega squared equals omega p squared. So is omega equals omega p. So we, and what does this describe? Basically, our oscillating quantities, for instance, the electric field, that if you remember in this linearization and complex notation, is a function of a given amplitude of the electric field of the wave times a to the I kx minus omega t. And in cold we see that, for instance, for k equals 0, then omega goes to omega p, and we have that the electric field actually is oscillating as I forgot omega p in this cold approximation for every k the dispersion rate should become this one here, and the wave number obviously goes to 0 in order to satisfy the relation. So only we don't have any the concept of a wavelength anymore or a k number, but we have the concept of local oscillation. So we see that the electric field is oscillating locally in each point in space with a given frequency, and this is the plasma frequency. Obviously, the electric field is just one of the things that is connected into this oscillation, and the other dynamical quantity which are oscillating at the same time in the same way are the electron density and the velocity of the electron as well, so the perturbation of the electrons. So we see that in the limit of cold plasma approximation, we in our solution only k equals 0 can satisfy this relation, and the wave is not a wave anymore, but we have that the wave is non-traveling. Non-traveling oscillation. And this is the plasma oscillation. Exactly what you studied at the beginning of the course, when we have two layers of electrons, actually a layer of electrons slightly displaced and recalled in place by the positive charge left behind when this layer of electron moves on one side and start initiating this motion of oscillation. The electrons are oscillating, so they are changing the density in time, which in turns correspond to a small perturbation in the velocity. So they are oscillating back and forth, and the charge imbalance that arises from this oscillation gives rise to the electric field. So we have all the three ingredients are present, but when the temperature of the plasma can be neglected, then this oscillation cannot travel. As soon as the plasma gets hot, so as soon as we relax this very strict oscillation, we take into consideration the fact that actually there's a thermal motion of the electron. The localized plasma oscillation we studied at the beginning of the course actually are becoming waves in plasma. So as soon as we can take into consideration the temperature, we see that the plasma frequency and the plasma oscillation are traveling waves. At which speed? At the characteristic speed of the wave. So if instead the temperature of the electron is different from 0, then we have that the characteristic velocity is different from 0. And then we have plasma waves. Okay. What is important to stress that in our derivation, which is based on, if you remember and go back, is based on the fact that we are describing the electrons as a fluid. And you might remember that the fluid description is valid up to a certain point. So there's a kinetic limit when we need a kinetic interpretation of the plasma, and the fluid equations are not adequate anymore for usually for very fast phenomena, or when the oscillation and charge imbalance occurs on a level which is comparable to the biosphere or the bio-length, then we recover again the fact that actually the plasma is not a continuum medium, but is made of charges, positive and negative charging. And we discovered the fact that actually these charges are moving here and there, and they introduce a charge imbalance, and the micro fields, electromagnetic microscopic fields that are living inside the biosphere. In that case, the fluid equation that we use for electron is not valid anymore. And what this means, that there's a limit in which actually our derivation is no longer valid. And this establishes a limit here where I'll put it directly into this plot. If the wavelength is too short, so and shorter than or equal to the bi-length, then the kinetic, the fluid description is not valid anymore, and we enter a region where we observe in a plasma what is called the Landau damping. So it means that waves that have too short wavelength are not propagating anymore. So we see that. Let's use a different color here, for instance, and draw a region on one side around the K vector, which is of the order of the reciprocal of the bi-length, 1 over lambda the bi, and on the other side, symmetric, obviously, is they are just same wavelength, but with negative sign for the regressive part. So 1 over lambda the bi, and we can highlight this region here, and we see that beyond this point, our derivation is shown to be not valid anymore. So and what is happening there is something that we are not going to describe in our course, but we see here that the waves are non-traveling anymore, are damped, and the phenomenon is called Landau damping. Which occurs for the wavelength of the lambda, or the wavelength of the wave, less or equal to the bi length in the plasma. So not all wavelength or wave number can propagate. We see a region where actually we see an electrostatic wave propagating. There's a point here around very long wavelengths where we see that actually the group velocity goes to 0, so almost is not propagating anymore. They are becoming just localized oscillation in this case. And there's an upper limit in wave number K, corresponding to when we sample the plasma dynamic on the scale length, which is of the order or smaller than the biosphere. So our treatment actually is not valid anymore. And what is happening is that any perturbation that can arise with that very high spatial frequency are locally damped. So they are not able to travel a long distance in the plasma. Okay, this is just for electron waves. longitudinal electronic waves. What happens if we take now into consideration the ions as well? So if we move onto a completely different time scales, because you remember for this derivation we said, okay, we make the electric field E interact with electrons, and during this very fast interaction, the ions are at rest. But the ions can interact themselves with the electric field, so we can actually obtain a very similar derivation for the ionic electrostatic waves. So actually what we see is that we can plot, represent in a schematic plot, 3 different kind of waves that we can produce in the plasma. Let's call this plot longitudinal waves in a plasma. So we consider 3 kinds of longitudinal waves. The first one is the wave due to electron motion. So we have a dispersion relation. Let's give it a color code scheme. So let's use, for instance, red for electrons. So we have omega squared equals to omega E, the electron plasma frequency, plus V0E squared K squared. And this is just the relation that we derived for the electrons. If we take into consideration the ion motion, then we get to a very similar equation. The derivation is basically the same. We neglect the interaction of the electrons, and we focus ourselves on the interaction of the ions with the electric field. And what you get is you get a similar relation, where here we have the omega pi, which is the plasma frequency for ions. So instead, it's the same formula of the plasma frequency, but instead of using the charge of the electron and the mass of the electron, we use the charge of the ion and the mass of the ion. And obviously, for analogy, we get a characteristic velocity of the ion squared K squared. And here again, this characteristic velocity is just gamma KB, temperature of the ions divided the mass of the ion. So it's very close to the thermal velocity of the ions. And then we have another dispersion relation with, let's use the green color here. So we have 3 curves, which is omega squared is the V sound, the characteristic speed of sound in the plasma times K squared. So where this V squared comes about, the Vs squared is the sound speed in the plasma. And if you remember from gas dynamics, the speed of sound is equal to gamma. Let's say, let's put it, okay, not just equal, but let's remember what it is. For a plasma, for a gas is gamma times the ratio of the local pressure of the gas divided rho, the density of the gas. And let's translate this into a plasma equation. So actually it's going to be, we have 2 species here. It's going to be gamma of the electrons times the pressure of the electrons plus the gamma of the ions times the pressure of the ions divided rho. Rho is the mass density. So we can express it as mass of the ion times the number density of the ion plus mass of the electron time the number density of the electrons. So Ne and I and E. Okay, why I put a different gamma for this these two species? Okay, what is going to represent this? This is the sound speed. So it's a description of refraction and compression that link together the plasma as a fluid. And these compression waves or acoustic waves are propagating inside the plasma at a given speed, which is given by this relation. If you go back, let's actually, we go back to our derivation of the longitudinal waves here. And if you remember, we say the wave solution are moving fast with respect to thermodynamic equilibrium times. So for the electronic wave, we use the adiabatic transformation. And this was the gamma of the adiabatic transformation. So when we go and redo the same argument for the acoustic wave, we discover that we have to think about which of the characteristic speed of acoustic waves. And what we find is that actually acoustic waves are isothermal for the electrons and are adiabatic for the ions. What does this mean? Adiabatic means that the wave phenomenon is too fast for thermal conduction to take place and redistribute the thermal energy inside the species. And that makes sense usually for fast waves with respect to the thermodynamic waves, thermodynamic times. So actually we see that acoustic waves are adiabatic for the ions. Let's use a nice color scheme. So we say that these are adiabatic, but they are slow compared to the characteristic time for, if you remember, that was the time of relaxation. So the time of relaxation for electrons in electron collision, so inside the electron species, is much faster than the equilibration time of the ions. So during an acoustic wave, the electrons are so can move so fast, can react so fast that actually we discover that for acoustic wave, the transformation for electron can be described as isothermal. So if you remember, the adiabatic gamma index is Cp over Cv, and is 5/3 for ions and electrons, as can be represented just like monoatomic gases, and the corresponding polytropic, let's say, or isothermal index corresponds to a gamma equals to 1 for isothermal transformation. Okay, so this gamma here, now we discover is not exactly the just the adiabatic usual index, but is the index of the polytropic transformation that correspond actually to the thermodynamic transformation that links the final and initial state of our species during the wave motion. And the initial state is the equilibrium state, and the final state is the perturbed state where we have the oscillation taking place. So all this then corresponds to, we can translate our acoustic speed. So we say that this gamma is 1 and this one here is 5/3 or whatever it is. depending on the dimension. So the first term becomes pressure of the electrons, and the pressure of the electron is the density of the electron times Kb, temperature of the electrons. The second one is the gamma of the ions times the pressure of the ions, and the pressure of the ions is density of the ion times Kb, temperature of the ions, divided by the densities. Let's leave it here, both of the terms, and now we do our simplifications. What can we simplify? Obviously, due to a large mass ratio here, we say that the mass of the electron is much smaller than the mass of the ion, whereas the density of these two species are of the same order of magnitude. If we are talking about a hydrogen plasma, then density of the hydrogen atoms, protons, is the same of the electrons. If this is not the case, but it's a different gas or medium that we got into plasma condition, then we have just a Z factor in front. So actually we can neglect the term, the contribution to the mass density arising from the mass of the electrons. And we can express here the density of the electron as Z times the density of the ions. So you see that we can simplify here, factor 3 pieces, and what we end up with is ZTE plus gamma for the ions, and then we have a Kb. Yes, let's put it here in front of Z. So we have Z KBTE plus gamma ions KB T ions divided the mass of the ion. Okay, and let's represent our 3 dispersion curves into a schematic plot as usual. So we plot omega of the wave as a function of the K number. So let's put here K and omega up here. And starting with red. Red is the electronic wave. So we have here, for instance, omega p for the electrons. And we have an asymptote here. Okay, let's make it a little bit lighter, maybe with a different color. One. Oops. Okay. And our curve goes as usual, one arm and the other one going this way. And we have that this omega here is the omega p, so it's the plasma frequency for the electrons. Then we have another relation, and we have for the ions and the corresponding omega p ions. So it's the plasma frequency for the ions, almost to take a break, time to take a break, and the the asymptotic speed is the almost the thermal velocity of the ion, and the curve is this one here. Okay. And finally, we have our third curve, which is going to be green. And you see this is a constant slope curve. So it's non-dispersive. We start from 0 and we'll draw it as a straight line coming out of the origin of the plot. The progressive and the regressive part. So we have that this goes as v speed times k. The asymptote here goes as v0 ion times k, and the asymptote here goes as v0e times k. And we have the electron wave. We have the sound or the acoustic wave. And we have the ion wave. And if we compare the three speed of the or characteristic speed of this wave, we see that the characteristic speed of the electrons is, then we have the speed of sound, then we have the ions, characteristic speed for the ion wave, and we see that the electron wave has a speed that is much higher than the speed of sound, and which is higher than the ion wave. Let's put this here, put a highlight, and let me just conclude here briefly, writing what is the, remember what is the characteristic speed for the electrons is gamma PE over the density rho E, same argument, and you get to the fact that this is gamma KB, temperature of the electron divided mass of the electron. And in blue, obviously, you have the same characteristic speed for ions in this case, which is going to be the gamma for the ions times KB, temperature of the ions divided mass of the ions. So final remark is we have three speeds here: the velocity of the electron wave, the ion wave, and the acoustic wave. Pay attention to this. Just that at the denominator we have for the electron wave the mass of the electron and the mass of the ion for the other two. So obviously, since the temperature are almost the same order of magnitude, okay, and K, the gamma and the Z are just the order of a unity, then we see that the major difference arises from the fact that for the electron wave, we have a denominator, the mass of the electron. So this is much larger than both the ion wave and of the acoustic wave. And you see that actually this numerator here is larger than this one here. So the way of ordering this waves is the one we presented here, and is corresponding to the slope of these three different lines arising, coming out of the origin. So this plot here is very dense, is full of details, and it summarizes in a single plot the fact that actually the plasma can sustain different kinds of wave. Let's take a break and reconvene here in 10 minutes time at 9:15 for a final remark on this plot, and then we start with electromagnetic waves. Okay. Here. Ready to start again? Are you? Still there? Is anybody there? Hello? Toc toc, tick toc.
Yes.
Okay. I have to check it every time because, you know, the connection might be lost and I'll be speaking for a couple of hours alone. Okay. Final remark. We have three different possibility for waves in a plasma that we are considering here, and we'll be having even more when we introduce at the end of the lecture today the electromagnetic waves as well. Here we have just considering the longitudinal waves, and we have the electron wave, the ion wave, and the acoustic wave. So you see that the plasma can sustain, can support many different waves of ways of wave propagation. And this means that the plasma will adapt itself to whatever the situation are. Here we are looking at this dispersion relation, which are, let's say, point relation. Obviously, by changing the moving from one point to the next one in the plasma, what could happen is that the temperature changes, and if the temperature changes, what is changing is the slope of these three lines. Obviously, if the temperature goes to zero, these lines are becoming even more and more horizontal, leading to the cold plasma approximation, where we do not have a propagation, but just localized oscillation. If instead the temperature is increasing, all these lines and these slopes are becoming more steep. And what it could change the density of the plasma. If the density of the plasma changes, you know that inside this plasma frequency here at the numerator, we have the density of the ions and of the electrons. So we change the value of these points here. So all these dispersion relation can change and vary along the plasma, reflecting what are the local plasma conditions. And you see that, for instance, if we consider now different waves, you see that very long waves, for instance, so for those waves that the K vector is zero, the electron wave and the ion wave are not propagating, are becoming oscillation. But a wave can be still there, and is the acoustic wave. So the acoustic wave, there's a region in K space for very long wave where the wave phenomenon is dominated by the acoustic waves. Then there's a region where, for instance, the electron waves that have much higher slope are dominating the phenomenon and are moving energy and momentum from one place to the next one, because they are much faster than the other ways. But the other ways can survive as well. So you see that the plasma is actually an environment where we have all kinds of waves interacting with each other, and there will be the possibility for what? For mixing together different kind of waves. And this is going to be what is called actually wave mixing, and will give rise to parametric instability, where one wave can be in resonance with another wave phenomenon, and exponentially amplify a given wave. So already just by looking at this very sketchy diagram of wave, we understand of the complexity of a plasma in carrying very many ways of oscillation and waves. So let's switch to the second solution for wave propagation in plasma, and this is going to be transverse waves. So we'll consider transverse waves, and in particular electromagnetic waves in plasma. And here again, let's spend a couple of seconds to analyze the name of these waves. They are not electrostatic anymore, are electro and magnetic. So this is already telling us that using the analogy that with the electrostatic term, and this time we have both the electric field and the magnetic field taking part into the wave. So both the components of the electromagnetic field will be propagated in the wave inside the plasma. And these kind of waves are transverse waves. So we are seeking for solution to the wave equation for transverse waves. So we are looking for solution where K vector is orthogonal to, for instance, the electric field. So first of all, let's analyze what is happening when there's an electromagnetic wave, so a light wave interacting with the plasma. We have to concentrate ourselves mainly and actually only in our course on the dynamic of electromagnetic wave and electrons, because the electrons are reacting and oscillating in the electromagnetic wave because they can respond to the very high frequency of the electromagnetic waves, whereas the ions are at rest. So we'll consider cold ions which are at rest. So let's analyze what is happening when an electromagnetic wave, as we know it, is interacting with an electron field, which an electron particle which is at rest in the plasma. So let's draw this cartoon where we have the propagation direction of the wave. Let's call it K direction. And if you remember, the property of the electric field and of the magnetic field for electromagnetic wave is that the Poynting vector, the vector defined by E cross B, is telling us the direction where in which the wave is propagating, and this is a light wave in vacuum, and the electric field and the magnetic field are perpendicular to each other, and the vector product is giving us the direction of the wave. So let's represent the electric field oscillation. So let's take some periods here, like that. And the electric field is oscillating in its own plane, like that. And these are the nodes of the electromagnetic wave. and the B field is oscillating in a perpendicular plane. So in perspective is this one here. So the E field, let's suppose to have it maximum here, goes like that. And then it changes direction. And this is the direction of the electric field. Let's use blue color for the magnetic field. Magnetic field here are somehow horizontal vectors that change the direction. Okay. And the plane of oscillation of the electric field is, let's say, in this case, a vertical plane in this plot, and the B field is oscillating in a horizontal plane. So that at each time we know that E cross B gives the Poynting vector, gives the direction in which the wave is moving, and you see that the wave goes. What is happening when this electric field is propagating, and okay, at which speed is this field propagating? Is propagating along the k direction at the speed of light, obviously. So let's suppose that we have an electron at a certain point here. Let's draw it like a mass point here, and let's put a frame of reference consistent with the propagation of the wave. So we put the x direction in the direction of the wave, the y direction in the direction of the electric field, and so this is the usual orthonormal basis. So x cross y gives the direction of z. And what is happening that when this field interacts and with electron, we have that the electron is reacting to the electric field and start going up and down in the perpendicular direction, in the y direction, mainly reacting to the force, the Coulomb force due to the electric field. So these are what the electron does is start moving up and down, and these are and it's not moving along x and z. It's just going up and down along y, and these are localized oscillations, and this motion is called quivering. So these are quivering oscillation. And how can we get this localized oscillation of the electron? We can just write the Newton's law for the electrons, for the single particle, where we have mass of the electron times the acceleration of the electron along y. So we just take the Newton's law in the direction of y. It's equal to minus E, the electric field along the y direction. And this becomes mass of the electron. The acceleration is the second derivative with respect to time of the position along y, equals minus E Ey. And actually we can solve for a kind of a wave equation, you know that the electric field is an amplitude times a plane wave. So we actually put here the wave term minus omega t. The fact that actually the electric field is oscillating in the y direction and the wave is propagating as a plane wave along the x direction. Okay. Now, the first term is just mass of the electron times the derivative with respect to time of the velocity. Okay. So this is becoming in complex notation minus I omega, the time derivative of mass of the electron, and let's call it Vy, so the velocity of the electron along the y direction. So by putting everything together, we can write that the velocity of the electron is equal to E charge of the electron times the amplitude of the electric field times A kx times A minus I omega t is I split into the part of spatial propagation and temporal evolution divided the mass of the electron times the omega, the frequency of the wave. So this here is just a constant phase term, okay? That depends on the position of the electron along the x direction, and that is fixed. So it's what we call a phase term. This is a given phase phi, and we can write it as E times the electric field, Ey, the amplitude, divided me omega times a phase term, A to the I phi, which is a constant, times the oscillating part, which is important to highlight, E to the I omega t. Oops. What this equation is telling us is that we found the solution that when the electron is hit by an electromagnetic wave, by a light wave, it starts oscillating up and down in the direction of the electric field. The amplitude of velocity oscillation is this one here. So the maximum oscillation is going to be the modulus of the quivering velocity. And so this is the V quivering, the characteristic amplitude of this oscillation for the velocity. Then we have a given factor that depends on as a phase factor, and then is telling us that the velocity of the electron is changing in time as a harmonic motion. So both the acceleration, the speed, the velocity, and the position of the electron are oscillating at the wave frequency. So actually we have a harmonic motion up and down along y of this electron, and the characteristic speed is the quivering velocity. Energetically, what does this mean? It means that when the electromagnetic wave is hitting an electron, which is previously was at rest in open space, it starts accelerating the electron, and the electron starts oscillating up and down, taking and giving back to the field its own energy. So on average, the position is not changing. The electron is oscillating around a fixed position, and it's not acquiring any particular contribution to the kinetic energy, and is continuously exchanging energy with the electric field. So half of the oscillation is taking energy from the electric field, and the other half of the electron, being an accelerated particle, is giving back to the field its own energy. So there's no net energy transfer from the electromagnetic wave and free electrons, unless the electrons are interacting with each other or with the ions. If they are just free charges in space, the electron will just start oscillating at the same frequency of the wave and absorbing and re-emitting the light intensity. So this is happening in empty space. What is happening when we have instead an electron inside the plasma? Before going to that, let's analyze a little bit the contribution of the B field. So initially, the electron is at rest. It will respond to the electric field. So it will be accelerated. If the electric field is up, then the acceleration will be obviously in the opposite direction because of the sign of the charge. But that doesn't matter. The electron will start going up and down. As soon as the electron starts oscillating, its own velocity will be different from zero and will have a contribution from the Lorentz force, which is V cross P. So in order to neglect this contribution to the actual motion, that it will become even more complicated if the amplitude of the quivering velocity increases, we are requiring that we can neglect the Lorentz force Okay, we want to be sure that we can neglect the modulus of the Lorentz force with respect to the intensity of the Coulomb force acting on the electron. And these two are proportional to the Lorentz force is minus E V cross P. So regardless of the orientation of V and B, we see that its modulus is proportional to the charge of the particle, so the elementary charge of the electron, times the typical velocity of the electron, times the intensity of the magnetic field of the wave. And the Lorentz force, the Coulomb force is proportional to the elementary charge times the amplitude of the electric field. Now we can simplify the electric charge, and we remember from general physics too that there's a relation between the amplitude of the B field and the electromagnetic and the electric field. You remember that B is in amplitude equal of E over C. So we have V of the electron, E over C divided E, the electric field. We can again factor out the electric field, and we see that V over C is a ratio representing actually the relative importance of the forces acting on the particle, in this case the electron, for the Lorentz term and for the Coulomb term. And we see that if we want to neglect the Lorentz force, we are asking that the typical velocity of the electron, which is the quivering velocity, is the order of magnitude of the oscillation in the electromagnetic field has to be much smaller than the speed of light. Okay, in that case, we can neglect what? The V cross B force. And this is true for the non-relativistic term, where when we speak about a relativistic interaction of electrons with the light wave is when the electric field, see here, is so intense that actually the quivering velocity becomes comparable to the speed of light. In that case, the Lorentz force term is becoming important and has to be included in the equation of motion. And the equation of motion is not that of a charge going up and down along the electric field, but is a more complex motion that is called figure 8. So like a figure number 8, because when we have we combine the fact that the electric field is making the electron going up and down, at the same time the magnetic field is deflecting it, and the resulting motion is called figure 8, like the number 8. And in all our derivation here, we will assume that we are working in the non-relativistic term. In our further derivation, we will assume the non-relativistic approximation or regime. So a regime where the intensity of the wave is slow enough not to take the electrons to quiver with a velocity comparable to the speed of light. Okay, so we have that this situation is applied to an electron which is in vacuum and is being hit by a photon, or actually not just a photon, and by an electromagnetic wave. So what we do now is to include the presence of the plasma. So let's come to the derivation of the dispersion relation. Of the dispersion for electromagnetic can be shortened as EM, electromagnetic waves in plasma. Okay, now the new ingredient that we add to our model is the presence of the plasma. So what are our assumptions? So let's we assume that the plasma is non-magnetized. In the sense of MHD, as you studied. So there's no externally applied magnetic field. Okay. Then another important assumption is the cold plasma. Approximation. It means that the thermal velocity is about 0, can be neglected. Then, obviously, we are seeking for solutions that are transverse waves. So we see four solutions where the K vector is orthogonal to the electric field, to the perturbation of the electric field, which is going to represent the wave. Okay, remember B naught and E naught are, we leave these symbols for the equilibrium state or for externally applied magnetic field. And instead here we use one for the perturbation, so the wave itself. And then since the quivering motion and the frequency of the wave's typical solution, allowed solution, are much faster than the time scale of motion of the ions, we can neglect the dynamical contribution of the ions to this phenomenon. So we can neglect the ions. This is because the mass of the ion is much larger than the mass of the electron. And so we say that this phenomena, the wave phenomena, are very fast. With respect to WRT ion characteristic time. Okay, then these are our assumption. We need our ingredients. Our ingredients are the equation that we want to mix in order to get a wave propagation. We've done that already when we, if you go back, for instance, at the beginning of this wave treatment, where was that? Something like this, okay? When we introduced wave in plasma, we stated that we need a Faraday's law for a source term for the electric field, a source term for the magnetic field, the Maxwell-Ampere's law, and then an equation that is telling us that we are not in vacuum but inside the plasma, so the microscopic Ohm's law. We are going to redo the same argument here and same derivation, but since taking, so it was a little bit far away in the lecture, we're going to rewrite the equation we need. So actually we need the Newton's law for the electrons, the Faraday's law. Oh, time to take a break. So let's just write the ingredient we need. We need Faraday's law, which is the source term for the electric field. Curl of E equals minus the time derivative of the B field. Then we need Maxwell's Ampere's law, which is the source term for the magnetic field and is mu naught J, the current density, plus the displacement current, mu naught epsilon naught, time derivative of the electric field. And then we are going to use the electron Newton's law, which is telling us that the motion of the electrons, the total time derivative of the electrons, V equals minus E times E, where we have the Coulomb force due to the electric field. We put the Lorentz force, but we are going to neglect it, as you know, because this is the a non-relativistic approximation, but anyway, we write at least once in order to remember what is the Lorentz force. And then we introduce a term that we are going to discuss after the break. And if you remember, when we derive the resistivity, we put in the Newton's law for the electrons a term which was a friction term. Okay, let's stop it here for 10 minutes till 10. So let's have some rest and then we'll discuss this. And obviously, then there's these three equations are combined together by the definition of the current J. So the current density J, which is linked to the velocity of the electrons and their own density. Okay, let's take a break and see you back in almost 10 minutes time at 10. Hello there. Ready for the last slot? Are there any questions about what we are doing right now? Is anybody there? Can you hear me?
Yes.
Oh, okay. No sign of life on the other side of the line. Okay. So if there are no questions, we can keep on going. And so we have three dynamical equations. And who's taking part into these electromagnetic waves? The electric field, the B field, and the electron. So we need a dynamical equation for all the three partners taking part into the wave phenomenon. And then we have to, let's say, definition of, add an extra equation, definition of density, of current density, that just links the electron motion to the source term for the magnetic field. So minus E and V. Okay. In the following, as you see, I'm not putting the index E for the electron, velocity of the electron, mass of the electron, density of the electron. Okay, we don't want to have a heavy notation here. So in the following, remember that everything is connected to plasma property is just about the electron species. So mass, velocity, density, all will be about the electrons. Okay, let's start working with this equation. And a final comment before proceeding is that in the Newton's law, if you remember, when we derived the electric resistivity, we didn't take into account this term, which we are going to neglect today as well. But we introduce a friction. So it's a competing phenomenon with respect to the acceleration of the electric field. So, and this is important term to reintroduce, and this is due to the collision of electrons with ions and with the other electrons. And if you remember this factor here, nu is the collision frequency. So we put everything together in this derivation where we have the electrons talking to the electromagnetic field, and then there's a way of energetically coupling the electrons to the plasma, because we have just shown in this derivation here that if electrons are not seeing each other, are not colliding, then there's no net energy transfer between the electromagnetic wave and the electron. And exactly this term here will be responsible for the energy exchange from the electromagnetic wave, from the light wave, for instance, of the laser. If we are using the laser, for instance, let's start speaking about light as laser, and the electrons, and the electrons with the ions. Okay. So this is the friction term. See the electric resistivity. Okay. Let's work a bit with the Newton's law, and let's write it as in terms of perturbation and linearization. So we can rewrite it in one go as we have, remember that we have the mass of the electron times the total derivative of the velocity. So we have derivative of the velocity plus the convective term, which is v dot grad applied to the velocity itself. And this is the total derivative equals minus E electric field minus E V cross B minus m of the electron, velocity of the electrons, collision frequency. Okay, pay attention in writing in with different symbols the velocity and nu, because it might be quite similar. And now let's add a perturbation symbol here. Remember that we are just taking into account the perturbation in our treatment, and let's neglect second order terms. You see here we have the product of V1 and V1, so we are going to neglect this second order term. Then we have another second order term here in the perturbation, and if we translate into complex notation, so translate into complex notation, I remember you means to expand the solution on a basis of plane waves, and then apply the differential operators to the plane waves, and this becomes then minus IL omega, this is time derivative of mass of the electron times the speed of the electron equals minus E1 minus mass of the electron, speed of the perturbation times the collision frequency. And we can then use this equation to express V1, the speed, the perturbation in electrons velocity, as a function of the electric field. So let me take it to the next page so you have it there. And I copy it here. So we have that V1 is equal to the electric field times the electron charge divided I, let's collect I times M, which multiplies, we have an omega here, and when we bring this onto the other side, we have a nu. So two different frequencies, we have omega plus I nu. Okay, so we see that there's a relation between the speed of electrons and the electric field, and it's a complex one. So the real part will be, let's say, the a redefinition of the amplitude of the speed of the electrons, and then there's a complex phase. So this will tell us that the speed of the electrons and the electric field will have a particular phase that depends on the collision frequency. So in certain condition, for certain omega values of the wave, the two are in phase or in opposition or in quadrature and so on. Okay, now let's do the same for Faraday's law and for Maxwell-Ampere's law. So we have, so let's highlight this. We are going to use this later on. This first, the first derivation for Newton's law for the electron. Now Faraday's law. So we have curl of E equals minus time derivative of B, and we are linearizing it and expressing it is as a function of the perturbation. Okay, now then we have the black color, Maxwell-Ampere's law is equal to mu naught J plus mu naught times epsilon naught is 1 over c squared, the time derivative of the electric field. And let's remember that we are working with the perturbation of all the three dynamical variables. So the magnetic field of the wave, the current density perturbation with respect to the equilibrium value, which is 0, if you remember. So J1 is linked to V1, and then we have the electric field. Okay, as usual, what we do is take the curl of one of these two curves in order to get to the wave equation. Before that, let's write the current density as well. So we have the J, the current density, let's leave 1 here, is equal to minus E charge of the electron times the density of the electron times the speed of the electron, the perturbation. Okay. And as I was anticipating, then we'll substitute for this term inside the J. Then, as usual, let's take the curl of Faraday's law, for instance, so we can have in the end the relation of containing the electric field only. So our program will be to express everything as a function of E1 of the electric field. So substituting and using the other equation to express B here, and then we have J and we have J here, which in turn is a function of V1, which is a function of E1. So the plan is clear. We want to end up with a single equation for the electric field only. Okay, and this is the usual vector identity. So we have the gradient of the divergence of E minus the Laplacian of the electric field. And this is equal to the curl of the second term, this one here. So it's equal to minus time derivative of the curl of B. We exchange as usual spatial derivative. We can swap them for the with the time derivative. Okay, now we can plug in here the Faraday's law. No, sorry, the Maxwell-Ampere's law. And we end up with, okay, we since we are we know where we are going to get, we want to describe waves, and the parameter that tells us about waves is the speed of light, okay, which in the end will be the characteristic speed for this wave. So we can express mu naught as a function of c squared and of epsilon. So we can actually say that mu naught is equal to 1 over epsilon naught c squared. And this becomes minus the time derivative of 1 over epsilon naught c squared j1 and then minus 1 over c squared, and we have the second derivative with respect to time of E1. Okay, now what we do is take this one here, we plug in here, and then we plug this into our equation. And what we end up with is, okay, let's translate this into the complex notation. So we have the gradient of the divergence of the electric field. So the gradient is IK, if you remember, that applies to the divergence of the electric field, which is becoming IK dot E1. Then we have minus the Laplacian. The Laplacian is becoming the square of IK. So minus minus becomes 1. So we have plus K squared E1. And please notice that we are retaining the vector information in this equation because actually we are not, using the fact that the electric field is at 90 degrees with respect to the direction of the wave. Then what we have the time derivative of the current minus the time derivative, so minus minus makes 1, so plus 1, plus I omega, and then we have epsilon naught c squared, and then we have j1. Did I put, okay, the timer is there, and plus what we have here. Okay, so here we have the second time derivative, so it becomes minus omega squared, but we have a minus in front, so we have plus 1 over c squared omega squared E1. And now we can plug in J our equation. Let's focus our attention on this term. So we are dealing with, or actually more than dealing, we are looking for solutions that are transverse solutions. So we want K vector to be perpendicular to the electric field. And that means that this term is 0 because K has to be perpendicular to 1. We are looking for transverse waves. So all this, the first term is 0, and what all that remains can be expressed as K squared A1 on the left-hand side. We can bring on the other electric field on the other side, minus omega squared over c squared E1 equals I omega over epsilon naught c squared J1. And we can multiply both sides by c squared. So we can have on the left-hand side c squared k squared minus omega squared times E1 equal I omega over epsilon naught times J1. Okay. Now you see that we have a part that is linked to the electric field. And on the right-hand side, we have the plasma presence. So let's suppose before moving into in a plasma, so substituting for the relation that links J1 to the electric field in the plasma via the resistivity, via the friction force due to the collisions. So let's suppose to be in vacuum and see what we get. So let's suppose to be in vacuum. Just in order to check that we are progressing in a good direction. So if we are in vacuum, J1 is equal to 0. In vacuum, there are no charges, there's no plasma, so there are no currents. So this relation is telling us that if we can have a wave solution in vacuum, and this solution is telling us that C squared, K squared, minus omega squared multiplied by the electric field is equal to 0. And the non-trivial solution, the one for which the electric field is different from 0, requires that our dispersion relation in vacuum is omega squared equals to C squared K squared. Okay, this is rather nice because what this dispersion relation is expressing a constant wave, a constant speed wave in a non-dispersive medium, vacuum, and the characteristic speed at which the wave is propagating is the speed of light. So actually we covered the electromagnetic waves in vacuum. So we see that the phase velocity equals the group velocity equals C. So we have wave electromagnetic waves in vacuum are propagating without dispersion at a constant speed, at the speed of light. Okay. So that's good. We recovered a result that we expected to find. And actually, if we represent our dispersion relation in vacuum, we found that we have the plus CK and minus CK direction. Actually, I should write it in a different color. So what we were using blue for the progressive direction. So this is blue. And then we have the regressive part of the dispersion relation, which is minus CK. And obviously this is omega as a function of the wave number. So any point on these two lines here are representing light waves in vacuum, and they sit on two lines whose slope is plus or minus C. So this is the part of progressive waves going along the K direction, or a given direction. So plane waves moving at the speed of light along the k direction, and the other ones are just representing waves. They are propagating in the opposite direction. Okay, and as we see, since the group velocity and the speed velocity are constant and are the same, we recall the fact that the vacuum is non-dispersive medium. Medium for what? For electromagnetic waves. And this is nice because we recover a result that is important and that actually occurs in practice, because what we are going to do, for instance, is to produce electromagnetic radiation away from the plasma, like light waves in the form of lasers or microwaves or radio waves, and then we send this radiation to the plasma, and so the electromagnetic wave will be produced, for instance, in a high vacuum, and when it starts propagating, it will be just light waves as we know them, but then they going to interact and enter the plasma. And if you remember, the outer layers are very rarefied layers of the plasma are called the corona, and then the propagation will be we smoothly change from a usual electromagnetic wave in vacuum onto a electromagnetic plasma wave inside the plasma. So we actually, in our experience, in our experimental labs, we are continuously producing and detecting radiation sent to the plasma and coming from the plasma, so that we always have this to take into consideration and take it into account. Okay, so now let's say we are inside the plasma. So let's move on to the electromagnetic wave inside the plasma. In this case, it means that J1 is different from 0. So we can define J1 as minus E n times the speed of the electrons. And we go and get this V1 here from Newton's law. Okay, so it's E electric field divided 1 m times omega and mu. So let's put it here, and it becomes minus E n, which multiplies, I remember it was, okay, E1, E charge times E electric field divided I unitary imaginary unit m of the electron times omega plus I mu. So this becomes, we can take this I on the top, and it's becoming just I. Then we have E squared, and we have the density of the electrons divided mass of the electrons, and omega plus I mu times the electric field. Okay, this is the J, the current density. And now we can plug it in our formula. So remember that we had, in absence of J, we had on the left-hand side C squared K squared minus omega squared that multiplies the electric field. And then what we had, let's go back. Oh, we had it I omega times J1 divided epsilon naught. So it was I omega divided epsilon naught times J1, which is becoming I E squared N divided M that multiplies omega plus I nu, and everything multiplied by E1. So you see that we are building our dispersion relation here, and okay, let me see if there's something missing. Okay, just the sign, but that is not what I was expecting. Okay, let's move on. So we have a minus here. I times I squared makes -1. Then we have E squared N divided epsilon naught times M. And then we have on top omega divided omega plus I nu times E1. Let's have a look at this guy here, this term. You see that this actually is the plasma frequency for the electrons. So we found again our friend, the square of the plasma frequency for the electrons. And we can bring this omega at the denominator. So we have 1 plus mu over omega. And let's put everything together. So we can have, obviously, as before, we are seeking for solution where E1 is non-trivial. So we can simplify this. And what it remains is the dispersion relation. And this dispersion relation is C squared K squared minus omega squared equals to minus omega E squared multiplies 1 divided 1 plus I nu over omega. Okay, let's rearrange it a bit. And for instance, let's have on the left-hand side the omega squared as we are used to write it. And this is becoming something like omega squared equals to omega p squared that multiplies 1 over 1 plus I nu over omega. And the other bit changes sign, it becomes C squared K squared. Okay. You see that we end up with is a complex dispersion relation. And since it's complex, we'll be learning that the imaginary part will correspond to properties of attenuation or amplification of the wave, whereas the real part will correspond to the propagation, so the oscillation of the wave. We can, and this is the dispersion relation expressed as omega as a function of k. But when we discuss about attenuation, it's interesting to analyze this relation as a in the other form. So as a function of k in terms of omega. So we can write it as another way of expressing the dispersion relation is the link between omega and the allowed case. So we can write that k squared instead of omega squared is going to be an omega over c squared. So actually we are solving for k squared on the right hand side, and we have then minus omega p squared divided c squared that multiplies 1 over 1 plus I mu over omega. Okay, and see this is another relation, dispersion relation, this time expressing k as a function of omega. And we see there's a complex factor here. So let's split into real and imaginary parts. Let's see how much time do we have. 3 minutes. Okay, it's a good moment to do this. And then on Friday, we'll analyze the propagation and the attenuation part of this relation. So we want to get the complex part. So we multiply by the complex conjugate here at the denominator. So we have the modulus on top, and we can get to k squared is equal to omega squared over c squared minus omega e squared over c squared. I said that we multiply by top and down by the complex conjugate. So we have 1 minus I over times mu over omega at the denominator, the modulus of that one. So it's going to be 1 plus mu squared divided omega squared. Now we have a real part and a pure imaginary part. We can separate them, and we say, let's put all the real part together. We have omega squared over c squared minus 1 over c squared omega e squared divided 1 plus mu squared over omega squared. And this is the real part. And then what we have minus, so we have a plus I that multiplies omega p squared divided c squared times mu over omega. Okay, so the first part, let's collect the two terms, and is the real part of k squared, and the second term is the imaginary part of k squared. So actually we can write k squared as real part of k squared plus I times the imaginary part of k squared. Okay. Is a complex quantity. And we see that the resulting K will be a complex quantity as well if its square is a complex quantity. So actually, K will be expressed as A plus IB. So we label A the real part of the K number and B the imaginary part of the K number. And we have the K squared will be a complex number as well, which we label A, capital A, and capital B. And let's focus our attention on this one here, and then on Friday we'll do the algebra to check what are the relation between these two real and imaginary part for the wave number and the square of the wave number. So suppose you have K written as A plus IB, then we can say that we have the K as a real part, KR plus I, KI, the imaginary part. And let's remember that our waves are described by an exponential of kx minus omega t. And let's plug this, knowing now that k is not a pure real number, but can be a complex number, and actually is a complex number when we are inside the plasma. So we express this as I k real plus I k I. Here, put the bracket, square bracket times x minus omega t. And we can split the real and imaginary part. So we see that we have I k real times x minus omega t times, then you see that we have I that collects another I here, so it's minus, becoming minus ki x. So when k is becoming complex, the real part is linked to, let's see, it was green. The real part is connected to the propagation property of the wave, and the imaginary part is linked to the attenuation. You see that this part here will select k vector, k numbers that have the real part that satisfy the dispersion relation. And the imaginary part instead will describe a factor that is exponentially decaying along the propagation direction of the wave, which is x, which is parallel to the k vector. So you see that this is describing the progressive exponential attenuation of the wave as the wave propagates inside the plasma. So here we'll on Friday, we'll describe the propagation properties first inside the plasma, and then we focus our attention on the fact that actually the intensity of the wave is gradually absorbed inside the plasma. So these terms here will allow us to describe a way of transferring energy from the electromagnetic wave to the plasma itself. Okay, I think it's more than enough for today. Is everything clear? Do you have any question about this algebra that we've been deriving, or are we fine? No questions then? Then we see each other on Friday. Have a nice day.
Arrivederci.
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 Arrivederci.